If you look at the diagram,
Yeah, carry on.
and then the amount of people, then this I think should, I don't know why it's so confusing. Is we. Zero and then carry out, okay, yeah, my bad, I forgot about this, so that's right. Yeah, so this is carry out one, carry out one goes into. Yeah.
This one's
This one.
and this is two.
No, two goes into three. I think that's why, I think this.
I think I am getting
This is the same
because then it should one.
above three. So this needs to change.
Like,
Yeah.
So this is just.
I think this is supposed to be two, and this is supposed to be three.
Like that.
Yeah, because it's. You're carrying out of one area, it's supposed to.
Unless you're eight. Eight. I'll try it.
Trying to think about.
Yeah. I mean, I've got it here.
Yeah, carry out zero.
Right.
And then carry out one will go to carry. Yeah, carry out the one goes to carry and you'll two. That allows it to. There's about two. And on so I. I got mine. I had one that changed in there. I had two things on here. And it was just need to, I got copies of sort of change that. So that it was.
Yes, these two are good. So this is.
Honestly, like, the only things that are bad, it's just, that's the big thing. Actually,
This one.
Yeah, exactly. I think that's fair. That's the main. Yeah. Nice. Good. And our math. Oh, so there's only one. I have.
He's like, yeah, patient there. The only thing is, I don't like this class structure. No, anymore. It's a great is.
Yeah.
It actually is pretty bad. It's like it, like, just let me more, so it's not just start framing.
They're back. So.
Okay, it's 9:30. A couple of things. I did grade, guys. I did grade your homework and quiz. You can see your grade on Gradescope. You can also see the mean and standard deviation. So the quiz grade was a little lower than expected. Question 1 wasn't a problem. It was mostly question 2. So that just means that if you aren't doing as well on that as you'd like, just spend a little bit more time reviewing your labs, and you should do better on the quiz. The other thing is homework. I guess I forgot to talk about it, but a lot of the homework submissions were not of the correct format. So the format that I'm expecting is the exact PDF that is on Canvas. So I don't want you to like write on a separate piece of paper and then just submit that like a screenshot, not screenshot, but a picture of the paper. If you would like to work on paper, just print it out and you can work on it directly as if it's a quiz like that. And you can also work on it electronically. I saw some people do that. But the main thing is it's a fixed template. So when I go to question 1 and grade it, everything is exactly where it's supposed to be, and Gradescope puts me right there. But question 1 wasn't really a problem, but if I went to question 2 and Gradescope is putting me on question 2, which is the 3rd page on the homework document, but if you did it on like a piece of paper, it could be still the 1st page, and it was expecting me to go there, and I had to go find your answers. So it's just supposed to be a fixed document. So please just do not modify the format of it. And when you submit to Gradescope, you don't have to select any pages that correspond to what question. Okay. So that's a minor thing. The main thing was the quiz. So there was one more thing. Someone did come up to me. They said that they kind of pulled the class about the quizzes, and we're going to re-poll and see if you guys still want Monday or would prefer Wednesday.
Wednesday.
Okay.
Because I actually couldn't do Wednesdays for whatever reason.
We did the same poll last time. Everyone said Monday. Yeah. Yeah. We have the recording.
Everyone's like, nah.
Yeah.
That was my
Okay.
bad.
And then the day of the quiz, everyone's like, we should have done Wednesday.
Okay, so we'll do Wednesday from now on. It gives you more time to work on the lab. You should be done with it because it's basically due 3 hours after our lecture, right? I think that is all then. Any other logistical questions you guys have? Oh, I have one, but I guess it wouldn't really be for now. But there are a few people that did not take quiz 1. So, oh, were you just not available? Okay, so if you are unavailable for a quiz and you know beforehand, you can tell me and we can take the quiz before, but there is no taking quiz after. Okay, and we do drop your lowest quiz, so it's kind of built in, like if you're sick that day, you can miss one, no problem. Okay, so combinational components, we're going to continue on with them. We know what a multiplexer or a mux is, right? It's just a selector. This is the digital logic circuit for it. And we also have the truth table for this 2 inputs mux. So we don't have to spend time on this. We also already looked at expanding the mux to be beyond 2 to 1, but selecting between 4 different inputs and 8 different inputs, right? And you can just generalize the logic equation to be the binary representation of the input that you want to select is your kind of implicant for that selection. And you just need to do that for all of them. Like this is 0, 0, right? That means 0. This is 0, 1, that means 1. This is 1, 0, that means 2. This is 1, 1, that means 3, right? And you can generalize that to any power of 2 size mux. And if you want to have multi-bit mux like you guys did in the lab, you used muxes to create a 2-bit mux, right? This was the previous lab, not the one that you're working on this week, right? So if you wanted to do that, it's as simple as just copy paste the mux, right? And all of the lower, like the 0 bit, go into one mux, all of the 1 bits go into the other mux, and now you have a multi-bit mux, right? So the thing that we want to expand on with these muxes today is using mux as general purpose logic. So a mux again is basically just a selector, and let's just use the A and B bits as our selector. And if we want to use this mux as general purpose logic, it's as simple as if I'm selecting 0, what does that mean that A and B are? Yeah, so they're both 0. So then if I take my equation, so A is 0, so A 0 and C is 0. B and 1, well, no, B is 0. So 0 and C naught is, and then 1 and C is C. So essentially, that means to implement this equation, if I select 0, I should select C. Whatever C is becomes my answer, right? So I can do the same thing, but if we're selecting 1, we get 0, 1. So in this case, A is again 0. So 0 and C is, but B is 1 now. So 1 and C naught. And then we have 1 and 0 and C is 0. So we put C naught if we select 1. And then for 2, so 1, 0. Now A is 1, so 1 and C is C. B is 0, 0 and C naught is. And then we have 0 and 1 and C is 0. So again, if we have 2, we are going to select C. And then for 3, our last one, A and B are both 1. So 1 and C is C. 1 and C naught. And then 0 and C. What does this simplify to? C or C naught? 1. So now we've used this 4-to-1 mux to implement this equation. Can we see this process? Okay. So you guys have.
What is that benefit?
It just is you're able to like reuse this logic block.
Oh, okay.
Work on this while I get your poll set up. So your poll code for day is 095. So do try this on your own first. Okay, I see some of us are still working on this, but in the interest of time, let's start with the peer discussion. So work with the people around you. And if you haven't finished, just finish with the people around you.
Yeah, because you said this.
Yeah.
It just means I was. I'm just like the internet. That's very small. It's not.
Yeah.
So this is on this.
This here.
And then you just kind of put the is certainly.
Sometimes.
But so this. Yes. Most of zero. All that. Zero, 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 one.
You can say it's like
Zero, 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 zero. This one was one better.
One zero.
One times zero. That's where it's there. And minus zero. Zero. That's like one is one. B of one. So that's what C is. It's like the other small.
Yes, you do. So, yeah.
So I was thinking it's just one line. And it's just I just still get easy. So like this was yes. Yes, it's in so something looking.
I hear that we're still working on this, but we do have to move on, so change your answer if you were convinced to change, and let's go over this together. So the way that I'm going to approach this question is I'm just going to test each one of these one at a time for each of these equations. One way that you can try and eliminate more at the same time is by starting with one of these inputs that simplifies a lot, because it's not always, it's more rare that you'll simplify all the way to 1. So let's just go start with this. So A is 0, B is 1, right? So this first term in this first equation is, this is, and then because this is 1 and all the others are OR gates, do we need to check anything else? This one checks out for this one, right? This first equation is, this second one is, so again, do we need to check anything else yet? This one still checks out. And then what about this one? This one? Here?
Or C.
What? 0. 0. So this one is eliminated, right? We don't need to check this one ever again. So down here, this is, this is
1.
And then because of the 1, we don't need to check anymore. It's still that, right? All right, so now let's just go, what? 0, 0. And then let's just erase this. And now we only need to check 3. So 0, 0, this becomes, and then this, right? So this is still working. We still get C. And then here we get, so this one does not work anymore, right? We don't need to check it anymore. And then the last one we need to check, C. So this one is still C, because C or C is C. So it still checks out 2. Now let's try input 2. We only have 2 equations to check. This becomes still 0, right? This is 0. This is C. This is 0. So this one is still working. This becomes 0, 0, 0, C. And then this is, it's 1, 0. So yeah, C not. So this is C or C not. So this becomes 1, which is not C. So this one doesn't work anymore. Right? So we just need to check between this one and none of the above. Does this one still work? So 1, 1. This is So C naught. So this one is implementing. The mux implements this equation. Right. Okay, so more applications of a mux is rather than just implement general purpose logic equations, I can also use a mux to make a logical function unit. So based on my selection inputs, I can do a different function, right? So if I select 0, my function is going to just always output 1. So I just connect a 1 to it, right? If I select 1, my function wants to do an OR. So all I need to do is draw an OR gate, right? And then A and B are connected to the OR gates. And now if I select 1, A and B, the OR gates is input on the 1 part here, and that gets connected to F, right? And then 2 is a NAND. So we can just draw a NAND gate connected to 2. And then we also have XOR. Connect that to 3. And then 4 is an XNOR. 5 is an AND. 6 is a NOR. And then 7 is just always 0. And then we have A, B connected to all of these, right? A, B. And now you have this functional unit that based on the selection bit can do different functions. So we see this application. So the opposite of a multiplexer is a demultiplexer. So in a demultiplexer, you have one input and you're connecting it to one of many outputs. So here's our implementation. And we can see that if we are selecting 0, 0, then we're just going to connect F to A. And the way that we achieve that is here we have A, and it's connected to this AND gates, and the connections from A and B are inverted. So if they're both 0, then it becomes basically 1 and F, which makes a F, right? And then all of these other ones are the other combinations. So B is 0, 1, 1, 0, and 1, 1. So if it's 0, 0, this one is always 0, always 0, always 0, right? And then same thing if we have 0, 1, all the other ones are all 0. So it's used to get one input connected to one of many outputs. Just the opposite of a mux. Okay. And decoders we've seen, and this is the simplest decoder, one hot output. So you have your binary representation as inputs, and that is the output that is turned to 1. So here we have 0, y of 0 is 1, everything else is 0. We have 1, y of 1 is 1, everything else is 0. And 2, y of 2 is 1, everything else is 0. And 3, y of 3 is 1, everything else is 0. So we've seen this before. And what I wanted to show you is that we can, again, use decoders in order to implement general purpose logic. just like we did with the mux. So if we have this equation, right? So y is a and b, or a naught and b naught, then all you have to do is essentially, with the one hot encoding, if it's 1 1, we know that the output here is going to be 1 0 0 0, right? So each one of these outputs can correspond to a minterm. So if we have the minterm AB, we connect that to an OR gate. And now if the input is corresponding to that minterm, we'll have it covered in our outputs. And again, for 0 0, that's A naught B naught. Now we have this decoder with just this OR gate attached to the end, implementing this logic equation. Does this make sense? So we'll see it again here. In this example, so we have our max terms are 0 to 4, and we have 3 inputs. So A, B, C, and then F is our output. So 1, 2, 3, 4, 1, 2, 3, 4, 2, 2. So we have 0, 2, 4, right? This is our equation, our truth table. And then we have 3 inputs. So we need a 3 to 8 decoder. So this is A, B, C. And there's our 8. This is 0, 1, 2, 3, 4, 5, 6, 7. Right? And we just want to connect the minterms that correspond to our truth table, right? So in this case, 1, 3, 5, 6, and 7 are our minterms. So 1, 3, 5, 7, and now this implements F. Are we good with this now? Making more sense?
That's what we're getting at.
Yes. Yes, I did not include 6. I missed it. Okay. So here are 3 more equations. I'll do the first one and the last one, and you guys can do the second one. So for the first one, we again just have this OR gate, right? And we're looking for the minterm. So this is 0, 1, 0, 1, which is just 5. So we grab 5, 0, 0, 1, 1, which is just 3, and 1, 1, 1, 1, which is just 15. And this is F1. So we see this? Right. So I'm going to erase this one. And then F3 is a little more tricky. It's not given to us as a min term, right? So we have to kind of figure out what this is referring to. It's given to us as a max term. And this is just basically the max term. It's 0 when my input is 1, 1, 1, 1. Right? And that means that it's 1 anywhere else. So we could implement this in 2 different ways. We could connect all of these. Right? And we have many, many of them. And this would be F3. Or rather than doing that, another valid way of doing this is, let's just make it a NOR gate and just connect this. Yes.
So the whole purpose of the decoders basically connect all the min term into a OR gate.
It's one application of using it. So I'm just showing, just like how I showed you that you can use the mux to make general purpose logic. I'm showing you that you can use this decoder as also general purpose logic. But another application is one that you saw in your lab, using it for the 7 segments. But that one is not a simple one hot decoder, right? So I'll leave you guys to work on F2. Answer anything to the poll once you're done working on it on your own. Mm-hmm.
All of these. And then if he was in there.
So 15 is only 1 when it's 1, 1, 1, 1, right? So I get 1 nor 0 is 0, right? Any other combination 15 is 0. 0 nor 0 is 1. So I've implemented my equation. And this is for F3.
If you have three variables, you just assume the last variable, you just put it 0 or 1.
What do you mean?
Like if you have, for example, ABC would be 1, 1, 1, then the last, you just put 0 at the end.
Oh no, the ABC covers how many midterms? So it is covering A, B, C, D, as well as A, B, C, D nuts.
It's listed like that.
It's not don't care. It's covering 2 midterms. It's like when on your K map, when you circled 2, so D is changing across them. So in that sense, we don't care what D is. Okay, but the output is not don't care.
Yeah.
That would be different. Okay, so I think we are done working on this, and we do need to get through more slides. So like I just did, right? The ABC, it's covering ABCD and ABCD naught. So here we're looking for 12, 15, and then ABCD naught is 14, and this would be F2, right? So the other thing is we already talked about this decoder application when we first talked about decoders. So what we should talk about is that we can create this tree of decoders. So we can use smaller decoders to make larger decoders, just like we saw that we could use smaller multiplexers to make larger multiplexers. So to do this, and this has to be the one-hot encoding decoder. You cannot do this with something like the 7-segment display. So you put your higher order bits to the first decoder, and then your lower input bits into the lower decoders. And now when these are, say, like all 0, right, that makes this one active. So we're enabling this decoder, and we're disabling all of these other decoders. So when they're disabled, that means that they just all output 0s. And now we use the lower order bits. If they're again all 0, then we have Y0 is 1, and all the rest are 0. But then if we have 0, 0, 1, then Y1 would be 1, the rest would be 0, and the rest are 0 because they're all disabled. So that's how you can use, yes.
Why does a 0 input for 5, 4, and 3 give a high? Oh, because the output of all those is it enables there. I got it.
Yeah.
Okay.
So this just tells you which one to enable,
Got it.
right? So like if this is 0, 0, 1, that means that this second one is the one that's enabled because the first one is handling 0 through 7. The second one is handling 8 through 15. Right? And so forth. Okay. So the next thing that we have not covered in lecture are encoders. So encoders are the opposite of decoders. So we're expecting only one of these to be 1. So it's a one-hot encoding on the inputs. And we just output the binary representation of which one was selected. So if we get 0 here, we should be outputting 0, 0, 0. If we get 1 here and the rest 0, we should be outputting 1, 0, 0. Just the binary representation of the one that is hot on our inputs, which number it was. And the implementation of this is, again, very simple. So just for y0, you're just looking at the numbers that need to have y0 as 1 for their binary representation. So in this case, it's all the odd numbers, right? Because y0 is for the first digits. So all of the odd numbers need y0 to be 1. So you OR all those together, and then you enable it. And then you do the same process for all of the other inputs. All right, so a comparator. So one way that we can do a comparator is just by checking that all of the bits are the same. So if A3 and B3 are the same, this would result in 1, right? The XNOR, because XOR is 0, 1 or 1, 0. So XNOR, it's 1 if it's 0, 0, 0 or 1, 1, right? And then we can do that for all of the bits in our comparison and AND them all together. And if the result of all of these are 1, then they're the same number, right? So that is a simple comparator. And then a comparator to check if things are less than is also fairly simple. You can just have A and B, 2's complement form, subtract B from A. If it's negative, A was small. If it's positive, A was bigger. And you do have to just have also some care with overflow. All right, so shifters. So we have logical shift, which is going to just, if we shift anything out, it's going to shift in zeros. So here we have logical shift right by 2. So we shift out this 0, 1, and we shift in these 2 zeros. And logical shift left, we're shifting in these 2 zeros, and we're shifting out the 1. And if you're not shifting any 1s out, logical shift right is divide by that power of 2. Like if I shift right by 2, that's divide by 4. And then if I shift left and I'm not shifting any 1s out, like this is not an example where it would work, but that is just multiply by that power of 2. So if I do, say 3, and I shift it left by 2, 3 times 4, this is 12. Right? Arithmetic shift is the same exact thing, except now we're maintaining our sign bit. So arithmetic left shift is exact same as logical shift because there's no sign bit to maintain. It just gets shifted out. But when you're shifting in from the left side with right shift, you maintain the sign bit by shifting in 1s rather than 0s if you're shifting right. And then you can also rotate. So this is rotate right by 2. So you can see that these 1s went over here. This 0, 1 went here. The 0 is over here. It rotated right by 2. The other one is rotate left by 2. Okay, so we're over by 1 minute. And this is the last slide. So we'll just cover this slide on Monday. Shamt is shift amount.
Okay.
I'm sure it's taken. It's used all over computer architecture.